Alright, in this video we're going to be looking at some of the basic concepts of probability. So what I need to do here is begin with some definitions of what probability is all about, and then we'll look at some examples that deal with some of the basic things that are related to probability. Okay, so we'll start off with some definitions. And one of them we'll start off with is event. What an event is just any collection of results or outcomes of a procedure. Okay. One event, for example, will be getting the heads on a fair on a fair coin, when you toss a fair coin, or rolling a 6 on a fair die. Those are considered to be events. Okay? Because that's a collection of results or outcomes of a procedure. Now, from an event, we have a simple event, and it is an outcome that cannot be further broken down into simpler components. Okay. That's what we mean by a simple event. Now, one example of a simple event would be if we have one birth, then the result could be one female. That's considered to be a simple event. Because for one birth, it could be either a male or a female. So that means that an event cannot be broken down into more simpler events. But let's say you had 3 births. Okay. So here this is a simple event. But with 3 births, let's say you had 2 girls and 1 boy. This is not a simple event. Because for 2 girls and 1 boy, I could have simpler events like this. The first one could be a girl, the second one would be a girl, and the third could be a boy. Or another event would be this. The first could be a girl, the second could be a boy, and the third could be a girl. Or another event, the first would be a boy, then the last 2 will be girls. Okay, because I can break that down into more simpler components. So having 3 births where 2 girls and 1 boy happens would not be a simple event. Okay. And then the next definition is a sample space. Okay. Every event, like tossing a fair coin or rolling a fair die, would have a sample event, sample space. Okay. So what the sample space is, it consists of all possible simple events. So in this case, a fair coin, its sample space would just be heads and tails, because you only have 2 faces on a coin, heads or tails on a fair coin. Now for a single fair die, here's your sample space. There's 6 numbers on the die, so 1, 2, 3, 4, 5, and 6 would be the sample space for tossing a single fair die. Okay. So those are just some definitions or some terminology that you need to be familiar with that deals with probability. Okay. Now the next thing I want to talk about is the notations for probability. When you have a capital P, that means probability. And then you have capital letters like A, B, C. Those denote specific events. And then this notation, where P with the A in the parentheses, for example, this represents the probability of event A occurring. So P with the A in the parentheses, or it could be P with a B in the parentheses or C in parentheses, whatever, that represents the probability of that specified event occurring. Okay. So that's the notation that's used in probabilities. Okay. Now next, we'll look at 3 different approaches to finding the probability. So here we have 3 approaches for finding the probability. One of them is the relative frequency approximation. Relative frequency approximation. Okay. With this one, you conduct or observe a procedure, and then you're going to count the number of times that event A actually occurs. Okay, so in other words, in this notation, probability that event A occurring would be this. I'm going to say the number of times that event A has occurred, and that's divided by the number of times the procedure was repeated. Example is this. Let's say I toss a fair coin 500 times, and I want to find the probability that I get heads after tossing a coin 500 times. This would be an example of a relative frequency approximation. What I would get is the number of times that I would get heads divided by the number of times I repeat that procedure, which in this case, for example, 500. Okay, so that's a relative frequency approximation. The second is called the classical approach. Okay. And this situation is where you're required equally likely outcomes. Okay. So here you're to assume that a given procedure has n different simple events, and that each of these simple events has an equal chance of happening. If the event A can occur, then we have this probability. So here the probability of event A will be the number of ways A can occur, and that's divided by the number of different simple events. In other words, they use S divided by N. And I'll give you an example of what a classical approach looks like. Let's say I have 3 different gumballs in a bag. Let's say 3 of them are blue, 6 of them are orange, and 11 are, let's say, green. And these are all gumballs in a bag. And let's say I want the probability. Now each one of them has an equal chance of being selected or an equal chance of happening. So if I want the probability of selecting an orange gumball, then I look at the number of ways I can get an orange gumball. There's 6 ways. And that's divided by the number of simple events. So here if I add the 3 and the 6, I'm going to get 9. 9 plus 11 will be 20. So that probability will be 6 out of 20. Okay, that's what we mean by the classical approach. Here are the number of ways that event A can happen, and you're dividing it by the number of different simple events. And then the third approach, now this one we will rarely use, is the subjective approach. Or subjective probabilities. Okay, and usually it's that probability of event A is going to be estimated by using knowledge of relevant circumstances. Okay. Like for example, if I have a math class, okay, and I have a 2-part math class, and let's say in the first part I have 20 students that are enrolled in that class for the spring semester. And then for the summer term, I end up getting only like 10 people that enroll for the summer. So usually, but from my subjective standpoint, from teaching a 2-part math class in the past, only half of those would get that take the first part, end up taking the second part in the summer. So that would be considered a subjective probability, which means I would expect that the probability of someone of having a class load in half would be 50%. But that's just an illustration of a subjective probability. Now, we will not use subjective probabilities in this course. We're only going to be using the relative frequency approach and the classical approach to probabilities. Okay. All right, next I want to talk about is complementary events. Alright, so here, for complementary events, we're going to be dealing with the complement of event A. So here, the complement of event A, the notation for that will be A with the bar on top. Okay, the complement of event A is going to be all of your outcomes in which event A does not occur. Okay. So in other words, define a complement if we know, well, let's say the probability of a complement. If we know the probability of event A occurring, then the probability of a complement will simply just be 1 minus the probability of event A occurring. Okay. So that's all there is to it. You just simply subtract the probability of event A happening from 1 to get the probability of the complement of event A. Okay, so in this first example that I'm going to talk about, so I might as well go ahead and bring that up. If A denotes some event, what does A bar denote? And we just got through talking about that. So here A bar is the complement of event A. Okay, so A bar represents the complement of event A. Now, if the probability of event A is going to be 0.005, is A bar unusual? Well, let's find. Well, actually, they ask this. If the probability of event A is 0.005, what is the probability of event A complement? Probability of A complement. So here, A complement, the probability of A complement is simply going to be 1 minus the probability of event A happening. So this will be 1 minus 0.005, which will end up being 0.995. So probability of event A occurring will be 0.995. Now in this case here, would A bar, or the complement of event A, be unusual? Okay. Now let's go ahead and talk about what unusual and usual events are going to be. Okay. So here's some definitions here. An event is unlikely if the probability is very small. And what do I mean by very small? Something like 0.05 or less. So we'll use that as a way of determining whether something is likely or unlikely. Okay, so back to that particular problem. We can see that the probability of event A would be unlikely or unusual. But for A bar, which is 0.95, it's not unusual. Okay. And that also brings up another thing. An event has an unusually low number of outcomes of a particular type, or an unusually high number of those outcomes, if that number is far from what we typically expect. So anything unusual would have an extreme result. Okay. Usually 0.05 or less. Usually it's got to be something very, very small. Or the outcomes have to be either unusually low or unusually high. Okay. Now I do need to and mention some principles and notation for probability. So let's start with some principles for probability. One is this. The probability of event A, for example, is going to be a fraction or decimal. Fraction or decimal. And it's usually going to be between 0 and 1. And that does include 0 and 1. Okay. So it's very important. The probability is always going to be a decimal between 0 and 1. And we can include 0 and 1 in it as well. Next, the probability. If your probability of event A is 0, that means you have an impossible event. That means it's not going to happen. Probability of event A being 0 means you have an impossible event. Let's say the probability of event A that's equal to 1, then that means that the event will happen. It is a certain event. In other words, it will happen. Okay. And then we already talked about the notation for event A. Usually it's going to be the P with the A in the parentheses. That means probability of event A occurring. And then we already talked about the complement where the event does not occur. It's going to be probability of A with a bar. That means the probability of the complement of event A. Okay. So those are very important because this next example deals with just that. And you want to find out which of the following values cannot be probabilities. Cannot be probabilities. Well, 1 can be a probability because we can include 1 in this because probabilities can be between 0 and 1, and that does include 1. But the square root of 2 is not. Because if you do the square root of 2 on the calculator, you're going to get 1.414, which is bigger than 1. Negative 0.55 is not a probability because probabilities can't be negative. 0.05 would work because that's between 0 and 1. 1.15 would not. Because 1.15 is a value bigger than 1. Probabilities has to be a decimal value or a fraction between 0 and 1. Well, 3/5 is can be a probability because that's between 0 and 1. 0 is also a probability because we can include 0 and 1 in that particular interval for probabilities, but for 5/3, that's like 1 2/3, and 1 2/3 is bigger than 1, so 5/3 would not be considered a probability. So these are the values that cannot be probabilities in this situation. Okay. All right. Now the next example deals with the complement in a real situation where you have 17 of the 100 digital video recorders or DVRs in an inventory are known to be defective. What is the probability you randomly select an item that is not defective? Okay. So let's find the probability of an item being defective. Well, we know 17 out of 100 is defective, so we have this as 17 over 100, and as a decimal that will be 0.17. Just do 17 divided by 100 on the calculator, you'll see that you'll get 0.17. Alright, next is finding the complement of that. That's the probability of it not being defective. So it's simply 1 minus 0.17. So if you do 1 minus 0.17, you're going to get 0.83, which means that the probability that the item that you randomly select that is not defective will be 0.83, or you can think of it as an 83% chance that you select an item that's not going to be defective. Okay, now let's look at some more. Well, here's another example dealing with probability. In a certain weather forecast, the chance of a thunderstorm is stated as 18%. Express the indicated degree of likelihood as a probability value between 0 and 1 inclusive. So here we can say that the probability of a thunderstorm, and we're going to write this as a decimal value between 0 and 1. So 18% as a decimal would simply be 0.18. And that's all there is to it. So the probability of a thunderstorm happening will be 0.18, or an 18% chance of a thunderstorm. Okay. All right, here's some additional examples. Now let's say you had a situation like this. Refer to the sample data for pre-employment drug screening shown below. If one of the subjects is randomly selected, what is the probability that the test result is a false positive? And who would suffer from a false positive result? And why? Okay, so here's what the table looks like. And what I'm going to do here is put the totals for each column going up and down, and totals going across. So 45 and 2 will be 47. 11 and 37 will be 48. And then I'm going to add across. 45 and 11 will be 56. And 2 and 37 will be 39. And that grand total will be 95, going straight up and down and going straight across. Okay, so here we want the probability of getting a false positive result. And what do we mean by a false positive result? That means that the subject did not use drugs, but the test came back positive. And by looking at this, here the subject is not a drug user, and drug use is indicated, meaning there was a positive test result. That number there is 2. And this is out of the grand total of 95. So the probability of getting a false positive test result would be 2 over 95. Now, with probabilities, we're going to round to 3 decimal places. So it'll be 0.021. Now, in the homework, they do ask you to round to a certain number of decimal places, usually to 3 decimal places when we're dealing with probabilities here. So that probability here will be 0.021. And who would suffer from a false positive result? Well, it would be that person that didn't use the drugs and the test came back positive. So that person tested would suffer, because he or she would be suspected of using drugs when in reality he or she did not use drugs. So here, subject's not a drug user, but the test came back positive. So those 2 people will suffer from a false positive result. Okay, here's another example. In a genetics experiment on peas, one sample of offspring contained 448 green peas and 171 yellow peas. Based on those results, estimate the probability of getting an offspring pea that is green. is the result reasonably close to the value of 3/4 than was expected? Okay, so we have 448 green peas and 171 yellow peas. So if we add those two numbers together, we get 619 peas total. Okay, so now we want the probability of getting a green pea. And in this case, there were 448 green peas, so that's going to be 448 divided by the grand total number of peas, that's 619. So 448 divided by 619 to 3 decimal places, that will be 0.724. So you just do it in the calculator, 448 divided by 619, which will be 0.724 rounded to 3 decimal places. So the probability of getting an offspring pea that is green will be 0.724. And is that reasonably close to the 3/4 that was expected? Well, 3/4 is 0.75, and 0.74 is close to it, so we can say that yes, it is reasonably close. Because if you do 3/4, you'll get 0.75, which is, well, 0.724 is close to that. Okay, here's another example. In a survey of 170 respondents, 170 respondents say that they never use a credit card. 1,221 said that they use it sometimes, and 2,833 said that they use it frequently. What is the probability that a randomly selected person uses a credit card frequently? Is it unlikely for someone to use a credit card frequently? How are all the results affected by the fact that the responses were obtained by those who decided to respond to a survey posted on the internet? Okay, so let's add up the 170 that say they never used a credit card to the 1,221 that use it sometimes and the 2,833 that use it frequently. And that sum is 4,224. So we're looking at a survey of 4,224 respondents. And then we want the probability that this person is a frequent credit card user. Well, we know that 2,833 say that they use it frequently, so that's your numerator, divided by the denominator of 4,224. That's the total number that responded in the survey. And to 3 decimal places, if you do 2,833 divided by 4,224, you'll get 0.671. So the probability that a randomly selected person uses a credit card frequently will be 0.671. Okay, now is it unlikely for someone to use a credit card frequently? Well, actually, 0.671 would be bigger than 0.05, which we use to determine whether or not it's unlikely. Anything unlikely would be less than 0.05. Here it is bigger than 0.05, so no, it is not unlikely. Okay, and that's because the probability is greater than 0.05. Used to determine whether or not an event is likely or unlikely. And in this case, since 0.671 is bigger than 0.05, it is not unlikely. Okay, now how are the results affected by the fact that the responses were obtained from those who decided to respond to a survey posted on the internet? Now, in this case, This is what we call a voluntary response sample, because these responses are based on those who choose to respond, which is not a good thing to use. So here, avoid voluntary response samples, because you're only going to get the responses from those who choose to respond on the internet, because it's not going to be the same. It's not going to be representative of everyone in that survey. Okay, so stay away from voluntary response samples. Okay, here's another example. To the right are the outcomes that are possible when a couple has 3 children. Refer to that list and find the probability of each event. So here, this is what the table looks like. Okay, now in part A, we run this. Among 3 children, there is exactly 1 girl. So here, we want the probability of exactly 1 girl. Okay. Now, exactly means only 1 girl in this particular situation. Now, if you look at this, we have a boy, and 1 girl. Okay, that's one event. The other one is right here, a boy, a girl, and a boy. That's exactly 1 girl. And this one right here, a girl, a boy, and a boy. There's exactly 1 girl in this particular situation. So here you have 1, 2, 3 different situations or 3 events where you have exactly 1 girl. And that's out of 8 events. So the probability of exactly 1 girl would be 3/8. Part B, we want the probability that among 3 children there are exactly 2 boys. Exactly 2 boys. Okay, now let's take a look at this. Exactly 2 boys, no more than 2 and no less. This one has exactly 2 boys, so that's 1 event. This event has exactly 2 boys, a boy, a girl, and a boy. That's 2. This one has exactly 2 boys in it, a girl, boy, and a boy. That's 3. And that will be it. So that probability of getting exactly 2 boys is 3 out of 8. And then part C, among 3 children there are exactly 3 girls. So we want the probability of exactly 3 girls. And in this case, if you look at it, there's only 1 event where you have exactly 3 girls. And this last one right here, the girl, girl, and girl. And there's only 1 event out of 8. So the probability of getting exactly 3 girls among 3 children would be 1 out of 8. Okay, example E9. If a couple were planning to have 3 children, the sample space summarizing the gender outcomes would be this: BBB, BBG, BGB, BGG, GBB, GBB, GBG, GGB, and GGG. Okay? Which is similar to the one that I just did in the previous example. Now you want to construct a similar sample space for the possible eye color outcomes using B for blue-eyed and G for green-eyed. Okay? And this is for 2 children. Okay? So here, we're going to say for the first child, you're either going to have someone that has blue eyes or green eyes. And then we'll expand that for the second child. If the first child has blue eyes, then the second child will either have blue eyes or green eyes. And then if the first child has green eyes, then for the second child, we'll have either blue eyes or green eyes. Okay? So that's what the similar sample space looks like. And usually I'd use a tree diagram for this. So here, these are all the outcomes. A blue eye and a blue-eyed child, a blue-eyed then a green-eyed, then a green-eyed and a blue-eyed, and then green-eyed and green-eyed. Okay, so those are all the possible outcomes here. So that sample space would just be this: BB, BG, GB, G, and G. Okay, so that's the sample space here. Now, we're going to use that to answer part B. Assuming that the outcomes listed in part A were equally likely, find the probability of getting 2 green-eyed children. Okay, so here we're looking for the probability of getting the first child with green eyes and the second child with green eyes. Notice there's only one way that we can get 2 children with both being green eyes. There's only one way out of 4. So that probability of getting 2 green-eyed children will be 1/4. And then part C is getting the probability of exactly 1 blue-eyed child and 1 green-eyed child. So here we're looking at the probability of getting a blue-eyed and a green-eyed, or a green-eyed and a blue-eyed child. Okay, so here this is a possibility of getting a 1 green-eyed child and 1 blue-eyed, and there's another possibility of a blue-eyed and a green-eyed child. So there are 2 ways out of 4. So that's 2 over 4. We can reduce that to 1/2. So the probability of getting exactly 1 blue-eyed child and 1 green-eyed child will be 1/2. Okay. Alright, there's one more concept that I need to cover in this particular section, and that's going to be odds. And sometimes odds are used in things like the racetrack or the lottery, or when you're placing bets. Usually they give you payoff odds. Okay? And there are a couple of definitions. Here you have the actual odds against. Event A. And it's going to be this ratio: the probability of A complement divided by the probability of event A happening. Okay? And sometimes they express this in the form of A with a colon and then B, which means A to B. And here A and B are integers with no common factors in them. And then you also have actual odds in favor. Of event A. That's just simply the reciprocal of the actual odds against event A. That's the probability of event A happening divided by the probability of A complement. Okay? So here the odds in favor will just simply be, if you were to write it like this, B to A. And then finally, you do have payoff odds. against event A. And that's the ratio of the net profit if you win to the amount of the bet. Okay, so the payoff odds event against event A will be this. The ratio of the net profit to the amount that you bet. Okay, so in this case here, if we look at this example that deals with payoff odds, here we got a modified roulette wheel with 28 slots. One is 0 and another is 0, 0, and the others are numbered 1 through 26 respectively. You are placing a bet that the outcome is an odd number, and in roulette, 0 and double 0 are neither odd nor even. So what is your probability of winning? Okay, so you're placing a bet that the outcome is going to be an odd number. So your probability of winning is this. Now 0, 0 is neither odd nor even. So we're only looking at, we're looking at all 28 slots. Now from 1 to 26, there are 13 odd numbers. So in this case here, the probability of winning will be 13 out of 28. Okay, the reason for that, because you have 13 odd numbers, 0 and double 0 are neither odd nor even, and there are 28 slots on a roulette wheel. So the probability of winning will be 13 out of 28. Now part B, they ask this question: what are the actual odds against winning? So here, the odds against winning is this. The probability of event A complement and the probability of event A happening. In other words, we're looking at the probability of you not winning, which is the complement of the probability of you winning, divided by the probability that you do win. So in this case here, for you not winning will be 1 minus the probability that you do win. That's 13 over 28. So you have 1 minus 13 over 28 divided by 13 over 28. Okay, so now we can use our calculator for this. Let me show you at inner fractions here. In this case, if I do 1 minus, now I'm going to use parentheses, 13 divided by 28, close parentheses. And then if I do the math key, which is on the far left-hand side, and then select number 1 for fraction, that's going to be 15 over 28. So that numerator is 15 28ths divided by 13 28ths. Okay, so now let's take that 15 over 28 and divide that by, and then in parentheses, 13 divided by 28, close parentheses. Then hit the math key again and select number 1 for fraction. That would be 15 over 13. So the odds against you winning will be 15 over 13. Now as a ratio, we write that as 15 to 13. So the actual odds against you winning will be 15 to 13. Now part C is this: when you bet that the outcome is an odd number, the payoff odds are 1 to 1. How much profit do you make if you bet $18 and win? Okay, so in this case here, let me pull this up. In this case, you have the payoff odds against winning. That's the ratio of the net profit to the amount of the bet. So in this case, the payoff odds were 1 to 1. And we're trying to find the net profit, so this is the net profit. 2, the amount of the bet was $18. Okay, now if we were to write this as a proportion, 1 to 1 would be 1 over 1. And then net profit to 18 would just be the net profit in the numerator, and 18 in the denominator. Now if you do any cross multiplication here, 1 times the net profit would be the net profit. And that's equal to 1 times 18, which would be $18. So here the net profit would be $18 if you were to just bet $18 here. And that payoff odds were 1 to 1. Now part D. How much profit should you make on an $18 bet if you could somehow convince the casino to change the payoff odds so that they are the same as the actual odds against winning? Well, here in part B, the actual odds against winning was 15 to 13. That's what we came up with in part B. So in this case here, $15 to 13, that's equal to the net profit to the $18. Here I'm using the same setup right here that I used in part C, but I'm using the payoff odds against winning would be 15 to 13. Now 15 to 13 as a fraction would be 15 over 13. That's equal to, let's see, the net profit, I'm going to let X be the net profit. So here X is equal to the net profit. And then the 18 will be in the denominator. Okay. So to get the X by itself, what I'll do here is multiply both sides by 18. So this will be X by itself, or the net profit. And then you'll do 18 times 15 divided by 13, which will give you, if you were to round this off to 2 decimal places, if you're using, and since we're using dollars and cents, so we need to round to 2 decimal places, $20.77. So if you were to convince the casino to change the payoff odds to 15 to 13, then the net profit would be $20.77. Okay. Alright, so this will conclude this particular video on some of the basic concepts of probability.